Hi everyone, I'm Chenhao from University of Wisconsin-Madison. Welcome to my talk, Cache-Centric Multi-Resource Allocation for Storage Service. And thank everyone for still being around. In today's talk, I'm gonna tell you how to squeeze more performance from a shared cache budget through some bunny magic, and you will see what that means soon. So today, building a system in the cloud is getting easier and easier. The cloud service provider offer many well-modularized service components, and our job is connecting them. However, such a interconnect Lego system became increasingly challenging to share. More specifically, each subsystem has its own provision and pricing unit. For example, DynamoDB was priced by read or write unit, where each request consumes units based on their request sizes. So directly read from DynamoDB is very expensive. So to avoid a crazy bill from AWS, you may want to spawn an EC2 instance, hosting some Redis cluster to cache hot data so that you reduce the bill to DynamoDB. So for such a simple system, eventually you'll end up at least 4 types of resources to manage. Namely, you need to manage the Redis cache size, EC2 bandwidth, DynamoDB's read and write units. So the question is, for such a complex system, how are we going to share all these resources across tenants? So the naive approach is we simply partition every resource equally among tenants, such that everyone gets exactly 1/n of all resources. This is by definition fair, because it's as if there's no sharing happen and everyone exclusively owns its own portion. But it also misses many opportunities and is surely suboptimal because it can ignore the demand heterogeneity among tenants. Some tenants may demand more read units, some may demand more bandwidth. So can we do better? So it turns out that jointly allocating multiple resource types is not a new problem. DRF has already told us the right approach is to equalize the share of the dominant resource type of every tenant. So in this model, we denote a tenant's demand as a vector called demand vector, which compactly represents the resource required to make a unit of progress, say serve one request. Here we have a simple example where Alice consumes read and write unit in the ratio of 1 to 2, where Bob consumes is a ratio of 4 to 1. So with equal partition baseline, every tenant will get half read unit, half write units. So we see there's many underutilization between these tenants. So we say Alice is write dominated with many read unit underutilized, while Bob is read dominated. So with DRF, we see a much better, much higher utilization. So in this case, Ali gets 2/3 of total write units, and Bob gets 2/3 of read units. So eventually, both achieve 33% higher throughput. But so are we done? Unfortunately, no. So it turns out that DRF fails to solve our previous sharing problem because of cache. So first, cache itself does not really fit into DRF's model. DRF generally assuming that the throughput a tenant could achieve is linear to the resource that was allocated. For example, if I want twice of throughput, I need twice of read unit, twice of write unit, twice of bandwidth. But cache is much complex. Cache represents a complex and nonlinear relationship which present a complex and nonlinear relationship between throughput and cache sizes. For example, we can add a slightly more cache to make a tenant's working set fit, such that its miss ratio will drop dramatically, and then throughput will change dramatically. Moreover, cache also complicated the allocation of other resources. Let me explain what does that mean. So we can generally model a storage service as a figure on the left, where a caching layer sits on top of some persistent layer. This is a very general model. You can think about Redis on top of some backend database or page cache on top of SSD. So in this model, the step 2s only happen upon cache misses. This means that for every resource that below cache, its consumption will depend on the likelihood that step 2 happen, which is miss ratio. We call these resources as cache correlated resource. This means that if a tenant allocates a larger cache, it will have lower miss ratio and eventually have a lower demand. Effectively, the demand vector is not a vector of constant. It's a vector that was parameterized by the cache sizes. And that is the root of all the complexity. Cache not only bring out challenges, also bring opportunity. So consider we have a cache miss ratio showing on the left, which show how cache miss ratio change with different cache sizes. Suppose we want a target throughput of 20K requests per second, and with 60% of miss ratio, we will require 12K read units. Now we give it slightly more cache, such that its miss ratio dropped to 40%. Now we only require 8K read units per second, which is a huge saving. So this is an example showing that slightly more cache can bring us a good saving on the other cache correlated resources, but the problem is, how are we going to get this slightly more cache? So spoiler alert, for the rest of the talk, I'm going to teach you how to steal these caches from your other peer tenants without pissing them off. Actually, they'll be happy about it. So the idea is based on a very simple observation that not every tenant benefits from cache equally. There are some cache-sensitive tenants whose miss ratio will change dramatically with the minor cache size changes, where there's some other cache-insensitive tenants where cache size change does not really reflect, does not trigger much miss ratio change. So technically, we have the opportunity to exploit the cache correlation and heterogeneous sensitivity among tenants. We can imagine that cache-insensitive tenants that donate some cache to some cache-sensitive tenant such that its demand on the cache correlated resource will drop. So we can take this saved resources and then benefit the cache-insensitive tenants. Ideally, we can eventually get a sweet spot such that everyone get higher throughput than they used to when we have partitioned the cache and other resources equally. But the problem is how much we're going to do this resource trading and what is a fair deal to do. So in our work, we make the following contribution. We first present an algorithm called HARE, which is based on universal abstract model about cache and other cache correlated resources. It tells you that given such a workload statistic, how to do allocation. And then to practice the generality of HARE in practical system, we build two systems as a case study. So HopperKV is a cloud-native KV cache, while BunnyFS is a local file system semi-microkernel. With different resources to manage, but they share the same core principle. For the time reason, I will only go over HopperKV, but feel free to check out our paper for the BunnyFS. So I will first go over how HARE, the algorithm works, and then explain how we're going to modify your practical system to utilize HARE, and followed by the evaluation and conclusion. So let's first see how HARE, the algorithm, works. So at a high level, HARE consists of like two phases. The first phase is called harvest, where you iteratively optimizing cache partition. And then the second phase is a redistribute phase. It will allocate the rest of resources to improve every tenant's throughput. Now let's dive into the algorithm. So to begin with, every tenant will simply start with a baseline allocation where every resource is equally partitioned. Recall this is by definition fair. Here for simplicity, we'll use an example where there's only two resources. You have a cache and a backend database, the read units. Now we start the harvest phase. So in the harvest phase, we're trying to iteratively relocate a chunk of cache between tenants such that all tenants maintain the same throughput as baseline, but in total, they will consume fewer read units. In this example, we're assuming that every iteration, we relocated one blue chunk of cache. So for Alice, given a chunk of cache, given an actual cache chunk, its miss ratio will decrease so that it will demand fewer read units for the same target throughput. Here, it can relinquish like three orange units of the 3 orange read units. So for Bob, if we take away a cache chunk, its miss ratio will increase. So to maintain the same throughput, it will require actual compensation of the read units. So in this case, they say it needs one extra orange unit. So since what Alice is happy to relinquish is higher what Bob requires for compensation, we say we make a deal between them. And we harvest the difference between what Alice relinquished and what Bob asked for compensation. Eventually, we exit the deal and we collect the difference in our harvest pool. So we repeat this process by relocating one chunk of cache at each iteration. So eventually, we will stop when we find there's no more profitable deal to make. This will conclude our harvest phase. So after harvest phase, every tenant will still have this throughput as if they're baseline. However, we have extra spare read units to allocate it. Then start the redistribute phase. The goal of this redistribute phase is to allocating the resource in the harvest pool weighted by what each tenant already owns. Here, Bob has twice the amount of read units than Alice, so Bob will get 2/3 of the harvest, and Alice will get 1/3 of the harvest. So after redistribute phase, every tenant will get like 1/7 of more read units, and thus they will get correspondingly an increase on their throughput. This example is obviously a very oversimplification where they only have one cache correlated resources. In our paper, we describe a complete version of HARE will support multiple cache correlated resources, and which is a full generalization of DRF. Feel free to check it out. Okay, now let me describing how we can modify a system to in practice so that it can utilize HARE. We take HopperKV as an example, but the methodology is universal and it's very transferable to many different systems. So to begin with, we have a cluster of Redis instance which cache data from backend DynamoDB. For better isolation, we use every tenant get a dedicated Redis instance. So HopperKV will introduce a Redis module, which is a piece of DOSO binary file that you can load into an unmodified Redis instance. Yes, you can still use apt to download your favorite Redis version without recompiling Redis yourself. And then this Redis module will handle these data plane get and set, and meanwhile it will collect the tenant's workload statistic. We then have an allocated daemon, which will collect every tenant's workload statistic from this Redis module, eventually feed this statistic into the HARE. We run the HARE algorithm, and then we adjust every Redis instance resource budget accordingly based on our algorithm output. So we have a few more practical challenges need to address for a system to actually works. For example, first, how are we going to know what each tenant's mix ratio be like if we have a different cache sizes? So we utilize a spatially sampled ghost cache, which will emulate the LRU with some sampled metadata. It was super lightweight with only nanosecond scale overhead. Second, workload can change over time, how we can adapt to it. Our solution is actually very simple. We run a new instance of HARE algorithm periodically based on very recent statistic, and we adjust allocation. We find the new allocation is significantly better. In reality, algorithm runtime is only a few microseconds, so like if you rerun allocation like every few seconds or every minute, the cost is negligible. Lastly, our estimated miss ratio curve is not always perfect accurate. There's a noise, and the cache miss ratio is static property, so sometimes there always sound like confidence interval. So the problem is how we're going to tolerate the noise and the accuracy. So in our paper, we describe a very elegant technique called MRC sorting. It's basically make sure that we always have a safe margin to tolerate the relative error so that the algorithm was still relatively stable. Due to time reason, I couldn't go over all these interesting details. Feel free to check out paper. Okay, now let's talk about the evaluation of HopperKV. So through evaluation, we want to know the following question. So in what scenario that the HARE, the algorithm, could achieve better performance compared to other alternatives? Can this HopperKV scale? Can HopperKV handle time-varying workloads? And how it perform under realistic workloads? So accordingly, we design a micro-benchmark to study under different wide spectrum of workload, how they perform. We design scaling, dynamic, and the real-world trace replay by micro-benchmark to demonstrate how it works. For the time reason, I will only show some selective results. Feel free to check our paper for more results. So we consider a workload with 4 tenants with YCSB workload. We compare it with the following comparison. In a baseline where every resource is equally partitioned, with DRF, which DRF managing every resource except cache, and we keep the cache at equally partitioned. And also the HARE will jointly allocating all the resources together. So we're first focus on the baseline, where all the resources are equally partitioned. Here we show the normalized throughput on the y-axis, so they're always 1 for the baseline. We label the absolute throughput on top of each bar. With DRF, the cache will remain unchanged, but each tenant will get higher throughput because we have a better distribution of read and write unit. In this workload, in this case specifically, CPS-A is write dominated, so we receive more write unit. Similarly, other 3 tenants are read dominated and receive more read unit. That's how the DRF get more gain. Well, HARE can further optimize the cache allocation according to the hotness, according to how each tenant benefits from cache, such that it will achieve much higher throughput compared to the pure DRF, with at least 1.7 improvement over baseline. Well, this result demonstrates that the benefits of how holistically allocating all resources with a uniform framework. We have other some like a very interesting takeaway in the paper. For example, we find that when every tenant had the same dominant resource, the DRF didn't really achieve much gain. But HARE can open up more opportunity by optimizing the cache allocation. Similarly, there are many other multi-tenant cache allocation frameworks which only managing cache, ignoring other resources. We find that usually you have to hurt one tenant to benefit others. But in contrast, HARE, by taking a holistic view of all resources together, we are able to guarantee there's no degradation for every tenant. So finally, let me conclude today's talk. So in this work, we formulate a cache-centric multi-resource allocation problem. As a solution, we present HARE. It's a generic algorithm to holistically allocating cache and other cache-correlated resources. We built 2 systems as a case study, HopperKV and BunnyFS, to show the utility of HARE in a practical system. More broadly, we would like to call for, from future, we should take a more holistic view about resource management. So instead of only allocating each individual resource, the holistic view enables us to capture the interaction between different resources, and eventually we can exploit them for better performance and fairness. With that, I conclude my talk, and I'm happy to take questions.